The very last type of equation that we'll learn how to solve this semester is a logarithmic equation. If you'll remember back to Unit 1, we began with simple linear equations in one variable. Then we learned quadratic equations, radical equations, rational exponent equations, rational equations, and exponential equations. So you've really learned how to solve a lot of different types of equations this semester. The key in solving any equation is to recognize which category does it belong to, and then once you know how to classify the equation, then you can apply an appropriate algorithm or process to solving it. In section 5.4.4, we will identify and solve logarithmic equations. Note, when solving logarithmic equations, you must check for extraneous solutions. Remember, we ran into these with radical equations. That is, you do all the algebra correctly, but you end up with an equation that doesn't balance the original. You end up with a solution that doesn't balance the original equation. You'll catch that with the process of substitution. How do we know if we have an extraneous solution for a logarithmic equation? Disregard solutions that create a negative argument in a logarithm. If you'll recall, the graph of a logarithm indicates that the domain is 0 to infinity. So here's a quick and really rough sketch of a logarithmic function. There's the vertical asymptote. Logarithmic function does something like this. So the domain of a logarithmic function is 0 to infinity. So anything that I plug into a logarithm must result in a positive argument in order to fit into the domain. Now, to remember the algorithm for solving logarithmic equations, I'm going to give you a really simple process. To solve, we are going to collect, condense, convert, and check. Collect, condense, convert, check. By collect, I mean get all of your logarithms together on one side. Condense, we're going to use our newly learned logarithmic properties to condense the logarithms into a single logarithm. Then we're going to convert to exponential form, and that's actually where we're applying the principle of inverses, getting out of log form into the inverse exponential form, and that'll allow us to solve the equation. And then, of course, we check. Example 5, solve the following logarithmic equations exactly. And we're going to use the process collect, condense, convert, check. In this case, the logarithm is by itself on one side. It is condensed into a single logarithm, so all we have to do is convert to exponential form. Recall that means we take the base of the logarithm, raise it to the exponent on the other side of the equals, and set it equal to the argument. So we have base 3 exponent 4 equals x. 3 to the 4th power equals 81. Therefore, we have solved the equation. Now, let's check this very quickly with our calculator. Remember the shortcut, you can press your math button and then alpha A to call up log base, and you can type in log base 3 of 81 and see we have a balanced equation. That's not so bad. The next example is even easier. Notice example B is not even a logarithmic equation. It is a linear equation because I have x to the power of 1. Notice a logarithmic equation contains a variable either in the argument or the base position. So the equation on example B has already been solved. We can evaluate log base 1/2 of 4 using our shortcut math alpha A log base 1/2 of 4, and we end up with -2. So x equals -2. Now, just to make sure you have an understanding of that process, let me relate it back to something we've already learned in this section. If I convert this to exponential form, base 1/2 to the x equals 4, we have 1/2 raised to the x power equals 4. That's an exponential equation. This is an exponential equation for which we can get like bases. So I'm going to write the left side. 1/2 is 2 to the -1, and we can write 4 as 2 squared. So notice we have 2 to the -x equals 2 squared. Therefore, our exponents must be equal. If -x equals 2, then x equals -2. So either way you look at it, we have solved the equation. Okay, let's practice this process again. collect, condense, convert, check. On example C, the logarithm has been collected on the left side. It is condensed into a single logarithm. So to solve, we are going to convert to exponential form. So we take base 2, exponent 5 equals argument 4x plus 1. The result here is a linear equation in one variable, so we can solve that linear equation by isolating x. Notice 2 to the 5th is 32. We can subtract 1 from both sides, and then we can divide both sides by 4. So our apparent solution looks like 31 over 4. Let's be sure and check it with our calculator. So I'm going to type in again the shortcut math alpha A log base 2 of 4 times x, which is 31 over 4 plus 1, and enter, and we have a balanced equation. So we are confident that that is the correct solution. Okay, those have been pretty simple so far. Let's look at example D. Notice example D is different because it does have 2 logarithmic expressions. So we're going to need to collect those logarithms on one side. So I'm going to add this logarithm to both sides. We end up with log base 5 of x plus 2 plus log base 5 of x minus 2 equals 1. I'm just adding the entire term as a collective on both sides. Next, we need to condense the logarithms. Here's where we apply our logarithmic properties. Since we are adding the logarithms, when we condense to a single logarithm, we need to multiply the arguments. So the first argument is x plus 2, the second argument is x minus 2, and I'm going to multiply those. Let's go ahead and FOIL those out. We would obtain x squared. Outside and inside terms, notice they would cancel, and the product of our last terms would be minus 4. Then we can convert to exponential form. Now, this is the part where your brain's going to kind of shut down if you're not familiar with log equations and say, what do I do next? Remember, when we solve equations, we're using the principle of inverses. What's the inverse? How do I undo that logarithmic operation? I use the inverse, which is an exponential operation. So I'm going to take base 5, exponent 1 equals x squared minus 4. Now the equation is no longer logarithmic. Now it is a quadratic equation. Since I can recognize that it's a quadratic equation, I know I've got 4 possible methods to solve the equation. The easiest method to use in this case would be the square root property. So we can add 4 to both sides. 5 to the first is 5 plus 4 gives us 9. And then we can take the square root of both sides, being careful to recognize the 2 roots there. So we have x equals plus or minus 3. Now, let's verify both of those solutions with our calculator. So I'm going to start with positive 3, and I'm going to plug 3 in for x on both sides of the equation. So math alpha A pulls up our log base. We can type in 5, and I'm plugging 3 in for x, so we have 3 plus 2. The value on the left side of the equation is 1. Now, let's check the value on the right side of the equation. 1 minus math alpha A, that gives us log base 5 of 3 minus 2. When we evaluate that, we also get a 1. So we know x equals 3 is a valid solution. We'll keep that one. Let's also check x equals negative 3. So I'm going to plug negative 3 into the logarithm over here on the left side, and notice what happens with your calculator. Your calculator gives you an imaginary output. So what's going on here is when we plug a negative number into this argument, we end up with a negative argument. And as we mentioned up here, the domain is 0 to infinity. You cannot plug anything into a logarithm that is negative. Those numbers are not in the domain. So we will exclude x equals negative 3 as extraneous, and we do not include that in the solution set. Notice also, if you're curious, if you plug negative 3 in over here on the right side, it would give you another negative argument on that side, so we could find it on both sides. Okay, on the next 2 examples, you can pause the video and work them on your own, or choose to work them right along with me. So they are logarithmic equations. Our algorithm is collect, condense, convert. The logarithms in this example have been collected on one side of the equation, so we're ready to condense. So we have log of the first argument x plus 9 times the second argument x. Since we are adding the logarithms, we convert that into multiplication in the argument position. Let's go ahead and multiply in the argument. We're going to apply a reverse distributive property here. We end up with x squared plus 9x equals 1. Now we're ready to convert to exponential form. Notice the base is not written in this example, so we will assume that it is the common base 10. So we're going to take base 10, exponent 1 equal to argument. And again, the logarithm has been eliminated by converting to exponential form. So we observe the result is now quadratic. So to solve this quadratic equation, we need it equal to 0. We can do this by subtracting 10 from both sides. This one is easy to factor as x plus 10 times x minus 1. So we have two apparent solutions. X equals negative 10 and x equals 1. Notice if I plug negative 10 into either of those arguments, I would get a negative argument for the logarithm. So that one is an extraneous solution. This one's very easy to check with your calculator because you can use your log base 10 button. So plugging in 1 for x, we have log of 1 plus 9 plus log of 1, and that balances to give us 1. So we have one solution for that equation. The next one is going to be a similar example, but instead of adding, we are subtracting the logarithms. So when we condense our logarithms, instead of multiplying the arguments, we will divide the arguments. But we will still recognize that it is base 10, and we will convert to exponential form. Base 10, exponent 1 equals argument. Now, this is a rational equation, and previously when we had a rational equation, our goal was to eliminate the denominator. And we can do that by multiplying both sides by that denominator. It's going to cancel it out on the right, and the problem of fractions will have disappeared. We have 10x equals x plus 9. This is a linear equation in one variable, again, where we started our semester. We know that to solve a linear equation, we're going to collect all our x's on one side, collect our constants on the other side. So we can subtract x from both sides. We get 9x equals 9. We can divide both sides by 9, and we end up with x equals 1. Again, because this is base 10, we can check it very easily with our log button, log log button. So log of 1 plus 9, make sure you close parentheses on your argument there, minus log of 1 gives us a balanced equation. So that one has one real solution as well. So that's the last new type of equation we will learn this semester. We have one more application problem to consider, and you are almost done with notes.